Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz, and I'm glad you've taken the time to join us today as we look at our topic of the Torque 101, a guide to fundamentals of torque control. And so this is going to be a little bit rudimentary or elementary as it may be about the principles of torque. We'll talk about why we use torque, the torque terminologies, and some definitions of those, and how torque is measured, and the different types of torque tools that are available to be used within the torque industry. So let's go ahead and jump right into it and get started. So what is torque? So the classic definition of torque is a measurement of a twisting or turning force. And this is usually done around an axis, but this is primarily the definition of what torque is. And you may see this in a number of different areas. You may hear of an engine producing so many foot-pounds of torque, or torque related to the output of an electric motor. In this case, we're talking about how much twisting or turning force is being produced. Now, when we use a torque tool on an application, torque is what we are measuring or what we are trying to achieve, but the end goal of what we are actually trying to achieve is going to be clamp force. And so clamp force is the amount or measurement that's generated by the tension that's indirectly controlled by an applied torque. So this is what we are trying to really achieve when we're using a torque tool. Is we're trying to achieve tension that allows us to be able to keep components together without them moving. And so this graphic kind of helps to explain what we are doing while we are using torque. So we have a bolted joint, and as we apply torque to the nut, it begins to stretch the fastener or the bolt and giving it bolt tension. And it's this tension that is actually creating the clamp force that we need to keep these components together without moving. And so this is the way that we achieve clamp force through torque. Now, there are other ways that you can produce tension, but they aren't very efficient for the assembly process. And so we use torque to generate the tension to give us the correct clamp force that we need within a bolted assembly. And this is primarily the whole reason that we use torque to be able to do those in the assembly process. So one thing that we need to keep in mind about the actual fastener that we are using is going to be its tensile strength. And so this is, if you think of the fastener as a little bit more rudimentary, is going to be as a rubber band. And as that fastener gets stretched, if we remove the tension that's on it, that fastener will return to its original shape. We can do that with the fastener as long as we stay within its tensile strength. And here's an example of a rod that's being pulled. And you can see at a certain point, the rod will begin to deform and then eventually break. And so in this case, we have reached its tensile strength when it is completely failed. But there is a point at which that fastener will no longer come back to its original size, and that is called the yield point. And once we hit that yield point, that fastener is susceptible to failure with any type of shock or any type of vibration that may happen that will cause that fastener to break. So as long as we stay below that yield point with that fastener, we stay within its elastic region, meaning that it will return to its original shape. And often you will see fasteners with their specifications that give a proof load of how many pounds of PSI it will take for that fastener to break. And typically we'll want our torque specifications for a given fastener to be within 75 or so percent of the proof load. And so this is the ideal of what we're doing when we're trying to create the correct clamp force. Is we want to be able to use that fastener correctly and stretch it just enough so it does not go into that yield point area and give you an issue where it might break. And so you'll see here that the fastener on the right has reached its yield point. If that fastener has been stretched past its yield point, it will no longer return to its original shape, as we see on the fastener on the left. So this is the idea of what we're trying to achieve with the actual bolted joint fastener. So how do we measure torque? Now, torque has a very simple formula to it. It's distance times the force, but there are a number of different things that go into the actual torque that's achieved. But on a basic level, this is what we are measuring. And so if we look at a fastener here where we have a wrench that we are applying force to, say, I believe we're going to be at 1 foot of distance, and we put 2 pounds of force on the 1 foot moment arm, then we are getting 2 foot-pounds of torque. Now, if we extend this out to 2 feet with the same 2 pounds of force, we have now increased our torque to 4 foot-pounds. And so this relationship is going to be primarily the same throughout the use of a specific tool or a specific amount of force that's being used. So in this event, if we wanted to pull our fastener, or excuse me, pull the wrench with 5 pounds of force, then we would have increased our torque to 10 foot-pounds of torque. And so this is how torque is usually measured. Now, we can also measure torque with the use of a torque analyzer. And the torque analyzer basically takes an analog signal and converts it to a digital signal that we can use to measure tools on torque assembly products through different types of sensors. And these sensors use what's called a strain gauge. And a strain gauge is a small little postage size stamp, basically electrified circuit. And the strain gauge allows us to be able to measure the resistance of the circuit as there may be a torsion applied to the actual strain gauge. And so here's an example of what one looks like on a piece of stock. So as there is a torsion in that stock, the electrified circuit is going to have different levels of resistance at different points within the torsional spread. And that is how we can then convert that signal from an analog to a digital signal. Here's another animation that explains it a little bit more visually. So we have our strain gauge that's laminated to our stock. And then as the stock will turn or get or tension is applied, the strain gauge will flex with that as well. Again, changing the resistance level and giving us our ability to see what the resistance change is from the standing state to a torsional state. And this is done through torque calibration. And so in this example here, you can see we have an analyzer that is hooked to a segment arm. And this arm can have different lengths to it. So we may be measuring, say this has a 2 foot arm on it. and we are then applying a load to the sensor and then allowing the system to calibrate the actual resistance that we are reading from the strain gauge to the analyzer. And at different points, we would then go ahead and measure that. And that is how we can use the torque analyzer to take that signal and convert it to a digital signal. And so in this case, there is a function which we call traceability. So the wheels and the arms and the weights that are used have to be calibrated to a certain standard. Those weights then are used on the torque analyzer, which has its own ISO specification and ratios. And then we have our tools, which have its own standard as well. And so if we use a tool on a calibrated torque analyzer, that is now traceable back to the wheels and weights and so forth. So you have the calibration traceability that takes place on the end result of the tool that then gets traced back all the way to the ISO specification of the wheels and the weights. So you have that traceability in the use of the tool, and that's what is done through the actual calibration process of the tool. So we have the analyzer that goes through its own calibration process, and the weights and so on and that go through and get more specific as they go through their own traceability. So that's going to bring us to units of measure. And so in our first example of how we used our distance times force, we used an imperial unit of measurement, which was primarily used in North America, where we have the units are going to be foot pounds, inch pounds, or inch ounces. You may also hear it said a little bit differently. It could be pounds feet or pounds inches, but primarily it's foot pounds, and inch ounces. Now, there are 12 inch pounds in one foot pound, and there are 16 inch ounces in one inch pound. And so it follows a lot of the same imperial units that we use with a little bit of ounces and pounds, and then also feet as well. So that is the imperial unit of measurement. And then we also have the international standard, which is done in either Newton meters, Newton centimeters, or Newton millimeters. And so this is a more widely used around the world international standard. And what does this mean compared to the imperial standard? And so if we have a moment arm here that is 1 meter in length, we would put the weight that's equal to 1 Newton at the end of that moment arm. And 1 Newton is the force needed to accelerate 1 kilogram of mass at the rate of 1 meter per second squared. And in pounds, that equals to 0.2248 pounds. And if we calculate that and convert that to an imperial unit, that's right around 8.8 inch pounds. So roughly 9 inch pounds or so for 1 Newton meter. And often people will think that the Newton meter is a metric standard, but it is really only half of the equation when it's dealing with metric. The actual metric standard for torque is going to be kilogram force centimeters, kilogram force meters, or gram force meters, or gram force centimeters. So that basically is the same, but we're using grams or kilos at the end of our moment arm at a certain distance for that particular unit of measurement. So there are different units of measurement that you may hear at one company or one outlet or another. If you do want to have a quick and easy way to convert them, you can go to our website. We have our conversion calculator available from any page. You can go in and put the unit of measurement that you have, convert that, and it will give you all of the torque values at any of those values that you may need as well. So if you do need that, the conversion calculator is available to you on our homepage or any page on our website. It is available from that. And so this is going to lead us into the different types of torque tools that can be used that you would see in the assembly process. And then the first is going to be torque screwdrivers. Now, torque screwdrivers operate just the same as a standard screwdriver is. The only difference is that once torque is achieved, that that screwdriver will simply slip or cam over, and the torque value has been reached. Now, there are a number, well, I wouldn't say a number, but there are a few different styles of torque screwdrivers that use different mechanisms to relay that torque has been achieved. In our torque screwdrivers, we use what is used in a number of different things, but it is basically a spring that is inside of the body of the tool. And as that tool is being, torque is being achieved, the spring gets compressed to a certain value. Then it will simply, the driver will cam and reset that spring so it can be used again. So once we get to the portion of the spring that is compressed, that is the torque value that we are achieved. And so the main difference between one brand of screwdriver versus another brand of screwdriver is how they go about compressing the spring. And in our case, we use a different method than a lot of other manufacturers, and that is the use of a radial cam within the body of the tool. So we have typically a 6-lobe cam with 3 ball bearings that ride inside that cam. As the screwdriver is pressed or turned, those ball bearings push in on a larger ball bearing, and that ball bearing is what is compressing our spring. This gives us a really smooth torquing action where we don't have a lot of force that is going when torque is applied, as opposed to some of the other methods of a ball clutch type of scenario. But that's going to be the main difference between screwdrivers and how those function. Now, there are different styles of screwdrivers. There are adjustables, are preset, and those can work with the same clutch mechanism that we have as well. Now, when we look at our next brand of torque tools, it's going to be the torque wrench. And if we look at this basically from left to right, we have a cam over style of wrench, which acts very much like a screwdriver does. When that wrench is pulled, it goes to a certain value and then the torque is achieved and that wrench simply slips. So these are wrenches that are used in really critical torque areas where you can't have the any over torque that may be put on by the operator. So these are a very operator friendly tool where you don't need the operator to be really careful when they're using the tool, as opposed to the click wrench. And we'll get to that here in just a second. But the next wrench to that is going to be a breakover style wrench. And so as this wrench is used, it breaks over, so the head will simply start to cam once torque is achieved with this style of wrench. Again, giving you, the operator, a very solid indication that torque has been achieved. Then the next style of wrench is the click wrench. The click wrench is a very good and accurate wrench. The most widely used wrench around the world. The only issue with the click wrench is that it is very operator dependent on the final torque that is achieved. Because if that wrench is being used by the operator and the operator doesn't hear the click, feel the click, or see it, and they keep pulling, they're adding additional torque to that assembly. And that can be very problematic, again, where you may have a critical type of torque that you need to achieve. So if the operator is very slow and deliberate and waiting for that, these wrenches can be very accurate, but again, they are very operator dependent on who might be using that, their mood or their size and strength. So again, the click wrench is a very operator dependent type of tool. Next is going to be the digital wrench, a digital torque wrench. And this acts very similar to a click wrench. However, there are more audible and visual signals that you may be getting close to your torque value, but there is no guarantee that where you stop is going to be the torque that you initially are looking for. That can only be achieved with the cam over style of wrench, that as that wrench is used, it simply slips and you can never over torque or never pull more torque than the cam will allow you to. So click wrenches, again, very, very popular tool that are used in the torquing process. The next tool is going to be electric torque screwdrivers. Now, these function the same way that the wrench and the screwdrivers do. They use a spring clutch mechanism that will apply a certain amount of torque to a assembly and then shut off once that has been achieved. So there are different styles and different kinds of drivers based off of the certain application requirements. And so you may have a really soft gaskety type of joint that may see some relaxation after the initial torque has been achieved. So we have a screwdriver that can provide a double hit mode where it torques out twice. So it'll click, click. And that second click will give you a better torque on the compression of that gasket. We have different drivers that have different RPMs that allow you to adjust those RPMs, that have a soft stop feature, a soft start feature. And again, those are all determined by the application, but a very, very popular choice for assembly as well. And so here's an example of the spring and clutch mechanism that is used on these types of tools. So that spring goes in the nose of the tool, and we can adjust the torque output based off of the spring that is in there. You can dial the cone, the nose cone up or down to adjust the torque value. And there are reference marks that are on the tool itself, so you can correspond that to a certain torque output. These numbers that are on the tool are not the torque value that the tool is producing. They are just, again, a reference point. But again, the torque screwdrivers, electric torque screwdrivers, very, very popular for assembly and use within the entire process. Next step up from the electric tools are going to be DC electric control tools. Now, these tools act very similar to the electric tools. However, they aren't controlled by a spring clutch. They're actually controlled either with a torque sensor that we talked about, the strain gauge when we measure the torque, or they're measured by current. So the amount of current draw is coordinated to the actual torque output. And the real advantage to a DC control tool is that word control. You get the ability to control everything that happens from the moment that the trigger is pulled until that assembly is over. So you can control the amount of RPM that happens. You can control the amount of RPM at different spots within the rundown. You can control the actual angle that may be used within that fastener. You also get to collect data that may be captured from that. You can use special modes that allow you to add different presets on top of each other. And then you can also create an entire assembly around that. because the unit does give you that ability to have multiple different presets within the tool. So in our case, on this on our EC or ECTD or our MD products, you can have up to 15 different presets that you can use throughout the range of one specific tool. So if you have a multiple torque setting within your assembly process, you can have one tool do that process because of the fact we can change to a different preset and use that tool for that assembly. Now, there are other advantages to using a DC tool. As I mentioned, there is data collection processes. There are digital inputs and outputs that allow you to communicate with line control devices, export that information to an MES system, and things like that. That you can also use in error-proofing systems to make sure that the operator is correctly giving the correct torque to a specific location based off of the readings from the tool. So there are a lot of advantages to using a DC-controlled type of tool. So the next is going to be pneumatic tools. Now, the advantage of a pneumatic tool is that you can go to a much higher torque value than you can with an electric tool. And so if you are doing things that require, up to you're in the hundreds of foot-pounds or hundreds of newton meters or so, you may use the pulse tool, which basically uses a hydraulic clutch type of assembly. But you could also use a standard pneumatic tool, which acts very similar to the spring clutch that we looked at through the electric torque screwdriver. But this is another option that you can use with the pneumatic style of tools at a higher torque value that you may need. And then finally, we have torque multipliers. And so what torque multiplier allows us to do is to be able to generate torque values in the thousands of foot-pounds all the way up to 100,000 foot-pounds if we need to. So we basically have an input source that is attached to a gearbox, and that gearbox can have a ratio of 4:1, 12:1, 36:1. It just depends on the amount of torque that we may need. And this is what is going to be generating that massive type of torque that we may need to, again, to stretch a bolt at a really high torque value to be able to create the tension that we need to make sure that bolt is available. And so we do have different styles. This is what you see here are electric versions. So we have an electric motor that has giving us our input, and then we have a gearbox. And then the little reaction arm that you see coming off the tool there is what is actually helping to generate the torque value. So that is holding the tool stable as it is producing the amount of torque that we need. Once that input value is met, the tool shuts off and we've reached our torque value. This can be available in electric like this. We also have a pneumatic style that uses a stall motor and PSI to determine its torque output, or you can even use a hand multiplier, again, depending on if that is going to be a 4:1, 8:1, 12:1. But you can see an example of that being used here on this flange connection for this, where we have a standard wrench that is being used as our input device, working its way through the gear package to generate the torque value that we would need for that. So again, that brings us all the way back to the beginning of why we use torque. And if there is anything that you get out of this presentation, I hope it is this, that we use torque to generate the tension in the fastener to create the clamp force that we need to go ahead and make sure that our assembly stays together and doesn't move, because any type of movement is going to create wear and possibly cause our fasteners to fail or we may be closer to that yield point. Again, with vibration or shock causing those fasteners to fail. So we want to make sure that we have the correct torque that's creating the correct tension and giving us the correct clamp force. So with that, that is going to end our presentation for today. And so we'll go to our questions and answers section with that. And so with that, Ashley, do we have any questions?
Thanks, Dave. Yeah, we have a couple questions here. The first one is, what is the maximum torque in foot-pounds for Mountz DC electric controlled tools?
So these, where you're going to see the DC tools, we have a max of 50 Newton meters for that. So we're going to be in that ballpark around 37 foot-pounds or so for those DC controlled tools.
All right, the next question, can we get a demo of how to use the torque analyzer with an electric torque driver? We might have some of this on our Learning Center, Dave, or another video somewhere, if you can't do it now.
Yeah, unfortunately, we have our trade show, which is going to be at the Assembly Show in Chicago next week. And my demo equipment is there. But we do have other videos of using our torque analyzer with a rundown adapter to get the torque from electric torque screwdrivers. Or if you like, we can certainly set up a time to show you that personally, if that is something that you'd like to look at.
All right, that's all we had for questions.
Awesome. Thank you so much for participating with us today. And we look forward to seeing you again at our next webinar. Thanks so much and have a great day.